In a distributed system, it is not possible to achieve availability and consistency at the same time when there are internal communication failures. Simplified, this is what the CAP theorem tells us. In the next few minutes, I will give you a little bit more detailed overview on what the CAP theorem is all about and what implications it has for the software architecture of modern web applications. Let's get started. Hi, my name is Bernhard. I'm a software engineer working in Vienna, and in this video we will take a closer look at one of the most fundamental principles in distributed systems, the CAP theorem. The CAP theorem deals with distributed systems, so basically with systems where multiple components are running on different machines and those components need to communicate with each other. Let's take a social networking app as an example. When you post a new picture on your phone, it is automatically transmitted to the social network's backend servers. Multiple servers, because a single machine cannot serve millions of users at the same time. So since we will have multiple servers, let's assume that we have one server per country, and all of the Austrian users are served by the Austrian server, and all of the Spanish users are served by the server in Spain. This whole social network is a distributed system because the individual servers need to work together to provide a single service to all of the users. Now, when you are the software architect of such a system, there is one difficult challenge you have to face. What if a user from Austria wants to view the photos of a user from Spain? We cannot have completely isolated regions. The servers of the different countries also need to communicate with each other to serve requests such as that one. So one way to solve this challenge would be that the server in Austria directly contacts the server in Spain for those images and then serves all the images back to the user that made the original request. For the user, the system would behave as if it were running on a single machine. You would send a single request to the server and get all of the pictures back in a single response. Now that we have established this context of a distributed system, what does the CAP theorem say about such a system? Well, it talks about two important properties of such a system, availability and consistency. And it states that those two properties cannot both be achieved at the same time when there are internal communication problems in that distributed system. So what is availability and what is consistency? Availability simply means that our system will return a success response when you send it a request. And it will also do so in a reasonable amount of time. So you probably would not call a system available when it delays your answer by 2 hours. Therefore, a system is unavailable if it returns an error or if it does not return an answer at all in the expected time. Consistency, on the other hand, is a little bit more difficult to define. Basically, it means that the distributed system is behaving like it would consist of only one node. So to give you an example, if you would publish a picture on your Austrian account, you would expect the application that this picture is also available in Spain and also available in Argentina. If this is not the case, and for example the picture is only available to your friends in Austria but not to your friends in Spain, this would be called inconsistent. In a more formal way, consistency means that all read operations provide the same value on all nodes and that this same value is also equal to the most recent write operation. Let's stay in our social network example and investigate the following use case. A user from Austria is friends with another user from Austria and one user from Spain. She logs into the smartphone app and wants to receive her image feed. In the background, this results in a request to the social network server in Austria, and this server in Austria can immediately respond with the images from her Austrian friend, but it does not have the images from her Spain friend because those are managed by the server in Spain. So to get those images, the Austrian server would contact the Spain server, fetch the images and then return them to the user. But what should the application do if such a communication between the Austrian and the Spanish server is not possible? For example, due to a broken network connection. This scenario is an example for a communication failure inside a distributed system, so the CAP theorem is applicable. Now, the CAP theorem tells us that no matter what creative solution we would find, there is provably no way to achieve availability and consistency in such a scenario. So there are basically now two ways to handle this situation. First, we can favor consistency and just return an error. We could, for example, tell the user, image feed is currently not available, please try again later. This would be consistent, but not available. The problem with this approach is that the more servers we have in a distributed system, the more likely it becomes that one of those servers becomes available at any point in time. So while this may be a solution for two servers and the outage of one server is a very rare occasion, this might no longer be true if you have dozens or hundreds or even thousands of servers globally. Therefore, at least in social networks, it is probably a better solution to return an inconsistent result, but stay available. So what could such an inconsistent result look like? Well, for example, in this use case, you could just return the images of the Austrian friend and leave out the images of the Spanish friend. At a later point in time, when the Spanish server is available again, the same user requesting the same image feed might then get a different list of images, even though none of her friends have added any content in the meantime. This is an inconsistent behavior, but provides availability in case of downtimes. So now that we have an intuition of what the CAP theorem is trying to tell us, let's put it in a more formal way. According to the Wikipedia definition, the CAP theorem states that it is impossible for a distributed data store to provide more than two of the following three guarantees. First, consistency. Every read receives the most recent write or an error. Availability. Every request receives a response without the guarantee that it contains the most recent write. 3. Partition tolerance. The system continues to operate despite an arbitrary number of dropped messages in the network. Now, looking at this definition of the CAP theorem, it is important to note that the original author of the CAP theorem, Eric Brewer, has admitted that this form of the CAP theorem might be misleading, because it states that there must be a trade-off. You can pick two of three, and the third one is partition tolerance, so you can't really not have that in a distributed system. So basically, you need to pick between availability and consistency. And when you see this definition for the first time, you might think that this trade-off must be made for a whole application. Well, that's not really how it works. First of all, partitions are a very rare event, so the CAP theorem does have nothing to say about the design of an application when there are no partitions. Second, the choice between availability and consistency does not have to be made at application level, but can be made for individual submodules or even more detailed for individual functions. So let's take an e-commerce application as an example. You could say that the payment module of that e-commerce application strongly favors consistency, because making payments in a correct and orderly way is very important, while for the reviewing module you could favor availability, because maybe a few of the most recent reviews could be missing. It's not a big deal. The remaining reviews are sufficient for most users. And you can also make those trade-offs based on individual functions. So for example, reading the most recent list of reviews could favor availability, because that's basically what I just described in the example before, while posting new reviews is maybe something that would favor consistency, because you don't want the user to lose the review they just wrote. And third, the author argues, is that being available and being consistent are not really binary attributes, so you are not either consistent or not consistent, but they are continuous properties. So in the consistency example of the social networking app before, you could have full consistency on the one side, where all posts and images are present in the exact right order, or you be fully inconsistent and have some of them missing completely. But you could also have something in between. You could have all of the posts and images, but maybe in the wrong order. This might be something that is acceptable for a social network, but not acceptable for a banking application. So in summary, this 2 out of 3 definition is too black and white. It's not that you can have only availability or consistency for a full application, but you can make this decision very often when defining architectures for such applications. So with all that being said, what should you take away from the CAP theorem? Well, in my opinion, the CAP theorem provides a very useful way of looking at the architecture of web applications. Whenever you see 2 different components or systems communicate, you should ask yourself, what would happen if this communication would go wrong? Is it acceptable if the application is completely unavailable when this fails? Or is there maybe something creative I can do to make the application not become unavailable, but maybe lose some of the consistency along the way? While this is a pure engineering problem, it really depends on the concrete requirements of the application and can lead to very creative solutions, which for me is one of the reasons I find distributed systems so fascinating. I hope this primer on the CAP theorem was useful for you. I heavily recommend reading some of the articles linked in the video description below. Thank you very much for watching and have a great day. Bye bye.